Okay, so um, we'll get started with today's lecture. I just wanted to check that you guys are able to see lecture slides that I've shared. Okay, that's great. So I'll just, in the interest of not switching too many windows, I'll not show the syllabus page at the moment. But if you look at the syllabus page offline, we are basically almost towards the end of the course. We have a assignment 5 due today, and then next week is essentially the due date for the project related materials. So your code and final report are due next week. And in the Excel sheet that I've shared on the that's there on the syllabus page, as well as you've seen it before, you will find the allocation of slots for each group. So slots cannot be changed. So try to make it to your slot, and 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 so you look at the slot duration and plan your presentation accordingly. Okay. So those are the two quick announcements I wanted to make. Any questions regarding that? Okay, so it looks like there are no questions. So then let's get started with today's objective. So what I'm going to do is, last time we spoke about k-means towards the end. So we'll continue in that direction, continue to look at unsupervised learning techniques. And so today we'll look at, again, a technique that some of you might have seen in 572, but it's worth while going through that in a little bit more detail from a potentially a different perspective, which is the notion of dimensionality reduction. And then in the second half, we will look at an extension to parameter estimation that we've seen before, maximum likelihood estimation. Sometimes that doesn't work, and so you have to use a different technique called expectation maximization. Modeling, which model class kind of gives us a challenge, and therefore look at the solution technique, which is expectation maximization. Okay, and then if we have time, we'll look at a couple of examples of at least the problem statements of a couple of different problems. One is called independent component analysis. The other one is called canonical correlation analysis. But it's not important to cover them. It's important for us to kind of go through PCA and EM as two tools. Okay, so that's the scope for today. And let me just switch over to the slides. Okay, so this is slide deck number 11. So let's come back to a step before, which is something that we recapped, last lecture also, which is we are currently in the domain of unsupervised learning. Okay, so last lecture was also about unsupervised learning. Today also we'll look at unsupervised learning. So unsupervised learning, the basic characteristic is that we don't have labels. And so we can either do, and our goal is generally to detect patterns from the data without the labels. And these patterns, one manifestation of these patterns is you can group things together, group vectors together or feature vectors together or whatever, the data points together. Okay. So one version is what it's shown in bracket is the hard version, where a vector can only belong to, or a data point can only belong to one group, or sometimes a vector can belong to multiple groups. So today we'll in fact look at a technique which for each data point provides says that whether the data point belongs to one group or the other, a exclusive choice. So you can be part of one, you could be part of multiple groups simultaneously. Okay, and so that technique is called Gaussian mixture models. It's just one technique among many techniques which do that. And so we'll look at Gaussian mixture models, and that's where EM will come into play in the second half of this today's lecture. Okay, so see, yeah, I'm trying to keep the chat window next to me so that I can actually see if there are any questions. So last time we saw k-means. So the question is, can we, what else can we do with our data which doesn't have labels? So we saw clustering last time, and today we'll actually look at two examples, as I said, two other things that you can do with data which doesn't have labels. One is dimensionality reduction, and the second one is density estimation. So, and the techniques we'll see in each bucket, we'll talk about it in a second. So clustering, just to recap, is what is the objective? In input is data, a bunch of data points. So xi is the ith data point, and let's say we have little n number of data points. There are no yi's. Okay, and what's our goal is to learn some pattern, as I've been mentioning before. In particular, the pattern is we want to separate data points into groups. That's what we want to achieve. And the examples here below list some techniques. We have only seen one technique, which is called k-means. The second technique here, it's called dirichlet process means. It's a generative model for doing the same type of, so it's a generative process for doing this grouping. And it has its own properties and pros and cons. The third name here, spectral clustering, is again another technique to group points into sets. Okay, so but we have only seen k-means so far. So that's the input, and that's the goal. Is basically separation of data points into groups. So what's dimensionality reduction? Again, the goal is is the same. You have a bunch of data points, and we want to learn hidden structure of the data. And in particular, in this version of the problem, the pattern will be we want to reduce the dimensions. Okay, so if our data point is 100 dimensions, maybe there are only a few dimensions which are actually driving all these 100 observations, 100 measurements we are seeing, or 100 attributes we are seeing. And so we want to get to those underlying dimensions. Okay, and so that's the informal goal, to reduce the dimensions, and you can make it concrete by explicitly defining an objective function and also the procedure. And so depending on the procedure, there are many different procedures. One of them, which is component analysis, is what we're going to look at. There are a few others. Topic modeling is a technique mostly used in natural language processing to learn the hidden structure of data. Similarly, multidimensional scaling and TSNE and autoencoders, they're all different techniques for somehow compressing your data set without the need for supervisor signals. So on the figure here, what you're seeing is something we'll explain in quite a bit of detail. So I will skip explaining this figure here for a second. So then dimensional reduction is something that we'll see for the first part, and then we'll look at density estimation right after that. So what is the goal of density estimation? Again, learn some pattern in the data because we don't have supervised signal. And in particular, what we focus on in this version of the problem is to learn the distribution that generated the data. So we'll make an assumption. It's not always needed that you need to make an assumption, but typically in this approach of working of unsupervised learning, you want to assume that, hey, there's some distribution that generated this data. I've observed the data. Now let me backtrack and figure out properties of this distribution, and which will give me a sense of the hidden structure of the data. Okay. And one of the examples here is mixture of Gaussians, which is what we'll see today. So what does mixture of Gaussians means? It's basically we're going to make Gaussian assumption on the data, that the data is actually drawn from a Gaussian distribution. And not just one Gaussian distribution, as the name suggests, it's a mixture of Gaussians. So the data can come from a joint distribution on data, which could look like this, which you can see at the bottom in the two-dimensional figure, in the bottom part, like where it says 2D density estimation. So you can see that there are two kind of peaks. This figure on the left is supposed to represent the probability density function, and so you can see the contours, and so you can see that there are two peaks here, which kind of suggests that there are probably two Gaussians which are mixed together to produce, and our data is represented by this mixture of two Gaussians. Okay. But density estimation is not just related to Gaussians. There are actually techniques that we've already seen before. So language modeling that we studied last time when we talked about estimating the multinomial distribution. So it was the same paragraph that we saw earlier, or a sentence that we saw earlier. The unigram model, the unigram model, and then the Markovian model that we saw. is also an example of density estimation because we are estimating the transition probabilities as well as the marginal probabilities of each word or each token. And there are also a bunch of other techniques that we will not get a chance to look at in today. One of them is called variational inference, which, if you focus on the plot on the right, it shows that, hey, there is some underlying distribution which maybe governs the data. For example, the observed data. What we do with variational inference is somehow set up an appropriate optimization function, optimize some parameters, such that at the end of that process, we'll get a distribution called the variational distribution that is shown in the dashed line. Okay. So via optimization technique, we will estimate a distribution which kind of estimates, which kind of approximates the distribution that we care about. Here, it's called posterior distribution. That's because there's going to be an appropriate definition of a likelihood and a prior and so on. Okay. But at the end of the day, it's a optimization-based technique to estimate a approximating distribution of data. Similarly, the last bullet point here is talking about Markov chain Monte Carlo. It's again a way to estimate. It's again a way to sample data points from a distribution on the data set. Okay, so in this case, instead of estimating parameters of a distribution, you have your original data, which is shown on the left-hand side of this figure. You have original data, like think of these as bars here. So this histogram. And then from that, you're not trying to get a closed form expression or some sort of a formula or some parameter estimates for the distribution of the data, but you just want to create a way to sample new data points from that distribution. So you're kind of sidestepping the explicit estimation of the distribution itself. Okay, so that's achieved. One of the ways to achieve it is using Markov chain Monte Carlo. But these are all examples of learning the density or the distribution of the data. Any questions about this class of problems that we've been seeing? I just mentioned two things. One was clustering that we saw last time. The two new things were dimensionality reduction, out of which we're going to pretty much be looking at linear dimensional reduction using principal component analysis, and then density estimation, out of which we'll be looking at mixture of Gaussians. And that's where expectation maximization technique will come in. Any questions? Okay, then none. Then let's proceed. So to summarize, let's connect it with the rest of the material that we've seen early on in this course. So here's a 2x2 grid. What I'm trying to show is as rows, I'm splitting the techniques that we've seen into supervised versus unsupervised. And on the columns, I'm splitting the techniques as discriminative versus generative. Okay. So you can see that the first cell, first of all, supervised versus unsupervised, there's an extra supervisor signal, which we are representing as y superscript I. If you focus on the supervised version or supervised row, then in the discriminative cell, you can see we focus on the conditional probability of y given x. And so we're not worried about the marginal distribution of x itself. So we only focused on decision boundaries. And so some examples are linear regression, logistic regression, and support vector machine. Okay. And the generative cell for supervised learning, which is what we saw, I guess, a few more recently, we have seen a few examples, naive-based model, which is what you are working on in the assignment. And then we've also seen linear discriminant analysis as well as quadratic discriminant analysis. So here we make an explicit assumption about the probability of x given y, or you can say that we kind of have a handle on the marginal probability of x, which is what p of x is. Okay. So those were the techniques that we saw. And then in the unsupervised row, we have seen one technique so far, which is k-mean. So it would be considered discriminative because it's not really modeling the density or the distribution of the data. Here, the data is just x's. So we're really not focused on modeling the distribution of the data, as in like estimating like some means and other parameters of a distribution that you would see. Instead, we're directly getting our objective, for example, the groups or the clusters. Okay. So here we have k-means, leadership process means, component analysis, spectral clustering, and so on. We'll see k-means, so we'll see component analysis right now. And in the generative cell for unsupervised learning, we are interested in, as generative just means that we are modeling everything that we see, which is this data set, via via a distribution on it. Okay. So in particular, we're going to have a distribution over X, and sometimes we will also have a distribution over what I call latent variables, or things which we don't observe. Okay. And so that's why there's an extra variable Z here. But for our purposes, all this generative cell is saying is that we're going to first go from data to a distribution on the data, and then do other things. Okay, so we have mixture of Gaussians as an example here. We also have topic models, which I briefly mentioned in the previous slide, variational inference, and Markov chain Monte Carlo. Okay. So let's come back to this cell for the first part, and then we'll switch over to the last cell, which is generative and unsupervised later. So if you have seen even in the last slide deck, the outline of the techniques was we were looking at k-means clustering, which we pretty much covered last time. We'll briefly recap today when it is needed. So today we'll start with principal component analysis, then go to mixture of Gaussians, and briefly mention expectation maximization technique to estimate the parameters of this model, which is the mixture of Gaussians. And if time permits, we'll briefly mention what the problems are, which are listed here. One is called independent component analysis, the other one is called canonical correlation analysis, and the last one is called kernel PCA. Okay. So let's start with principal component analysis. So principal component analysis, as we briefly discussed earlier, is an example of a dimensionality reduction technique. Okay. So, and even before getting into the technique, we want to briefly at least ponder about what is meant by dimensionality of the data. For example, you look at, so we're going to see a few examples of data on in two dimensions. And if you look at this data, you can see that, you can kind of get a sense of, hey, what is the dimension of this data? For example, this could be, one dimension. If I had chosen my, instead of x1, x2 like this, if I had chosen some other way of measuring, then maybe this data set just needs one number to represent each point instead of two numbers here. Similarly, now this is a different observation, different bunch of data points. Maybe here, it may be needed that you want to have two data points to represent, two coordinates to represent two attributes or two coordinates to represent each data point to kind of capture some trends or some patterns in this data set. Similarly, now, there's a third data set, again, in two dimensions. But this one, is a little bit tricky. So the question is, do you need two data points to represent this data approximately, or can you get away with just using one data point? And we'll come back to this question later, perhaps. And the last one is, if the data points really, at least visually are not giving any sense of a structure, then maybe you do need two coordinates, to represent each data point. Okay, so there's a point of view taken in dimensionality reduction approaches, which is that the data lies along what is called a low-dimensional manifold. Okay? Which just means that there is smaller coordinates in data. So each data point, let's say it's 100 dimension, can probably be represented using only 10-dimensional vectors. Okay, so each original vector, which is 100-dimensional, can be represented using potentially a 10-dimensional vector. Okay, so that's which means that the data actually, even though it's residing in some 100-dimensional vector space, it's actually not filling up that 100-dimensional vector space. Maybe it only lies on a plane. Okay, for example, right? Or maybe 90 of its coordinates are all zeros. Okay, which means that even though it's a 100-dimensional vector representation, you can kind of drop all the other 90 coordinates and you still have no loss in representation, for example. So we are using the word manifold here, and it's going to be informal for the purpose of this course. So what is a manifold? Manifold is just that it's basically a subset or subspace of the original space in which the data points lie. That subspace is such that locally at each point, its neighborhood resembles, can be thought of as just a Euclidean space. Okay, so just locally at each point, the neighborhood resembles an Euclidean space in the sense that you can, so it's a subset of the original space. So for example, think of this, right? So this, this, if you think of some region that you can draw around this data points, what I'm trying to say is that that region, if you take any point locally, it will look like it's a Euclidean space, although that subset itself is not a vector space, is not a proper vector space, right? This two-dimensional space is the vector space. So manifold just means, just think of that as like a surface in a higher dimensional space. So it may not, it may not have one-to-one mapping with Euclidean space or regular vector space is the second point. But let's look at some examples to kind of further understand what this, at least informally means. One-dimensional manifolds are lines and circles. So when those circle, right, it's not exactly a circle and not the inside, just the boundary, for example. It maybe needs two dimensions to kind of represent it. But if you look at a point and the region around it, it looks like a line, right? If you really zoom in. So so maybe you can think of it as a manifold. And again, two-dimensional manifold, again, something like surfaces of planes or surfaces of a sphere, like a golf ball or something. They can be thought of as a 2D manifold in the sense that they're living in 3 dimensions, for example, but they are not really 3-dimensional. They're kind of constrained, So, and you can think about the 4 examples in the previous slides. So for example, this one, you can think of this as really a 1-dimensional manifold in a 2-dimensional space, where it's really a circle here. Okay, so the objective of the previous slide is just to say that we're going to assume that, hey, there's a low dimensionality in this data set, which is the first point, and we want to now try to get to it, okay, using a procedure. So let's give an intuition for principal component analysis, and then we'll look at the full picture later. Okay, so next few slides, next few minutes, we're going to kind of really think through what is PCA doing by looking at simpler versions of the problem. And build our intuition. So let's say we have our data set. Again, xi's, they belong to n dimensions, and there are little m of them. And the intuition for like what we want to do is that, let's say they're for simplicity, let's say they're 2-dimensional in this illustration here. Then, we want to understand like what can we get away with if those two are, for example, strongly correlated, linearly correlated. For example, here is x1 versus x2. Maybe x1 varies. When x1 is high, x2 is also high, then maybe the red line is enough to represent these two coordinates. Maybe in the second center plot, maybe it's not, because it seems like they're not that correlated with each other. And similarly, in the last plot, which is the left on the right side, when x1 increases, x2 decreases. So maybe there's like negatively correlated with each other. Okay. So the leftmost and the rightmost situations is where maybe we can try to use this correlation as a way to detect and drop, drop in dimensionality. So let's think of, what we want, right? We want, for example, a smaller dimensional representation than the original n dimension. Okay, or in this illustration, we want, for example, a 1-dimensional representation instead of the original 2-dimensional representation. Right. So representation of this D, remember, is the data set. So instead of let's for n in this illustration is 2. So we want a 1-dimensional representation instead of 2-dimensional representation. And one option, at least in this illustration, because our data points are just 2-dimensional, is to choose a line, right, in the 2-dimension that best represents this data. Right? Choose a line. Right. So remember, line is 1-dimensional manifold in a 2-dimensional space. So we want to choose a line. How do we choose a line? We just have to choose a line such that each data point, there is a corresponding point on this line, right? So, there could be multiple lines, in this 2-dimensional space, these blue lines on the left side. If we pick one of these lines, basically, if you want, and we want to represent the original data points, we have to somehow assign for each of the original data point a point on this line, right? And then the question becomes, hey, which of these lines is the best new representation for the original data? Okay, so which of these lines is the best? And for that, when we talk about which of these lines is the best, there has to be some objective measure. So some optimization objective needs to be established. Okay. Okay, so let's start with really this line perspective, and so let's start with two-dimensional setting, and then and then maybe generalize it to the full principal component analysis procedure. So any questions so far? Okay, if there are no questions, so let's look at so we are really we're trying to really poke holes at our if you already know PCA, then this is a good exercise to think through PCA from a different perspective. So so with that, so let's try to stick with a particular example. Let's say the line that we care about is we want to represent it using, so a line in any dimensional space can be represented using two things. One, a point on the line, and a vector direction. Okay, a vector which provides basically direction. So B plus alpha u represents a line in any space, 2 dimensions or 10 dimensions, where alpha, you can think of that as a number on the real line. Okay, so B is a point, and u is a vector indicating the line's direction. And if you scale u to be small, then you get smaller, points like this. And so if your alpha is, let's say, 100, then you get a point which is higher. So basically, when alpha is negative, you get to the other side. So basically, when you change alpha, keep changing alpha, you get basically a line, okay, along the direction which is the direction of u. And so what we want to achieve then is go from each of the original data point xi to a new point x prime I. So xi to x prime I, where x prime I has to be, since x prime I belongs to the line, then it should be equal to beta. Sorry, which it should be equal to b, which is which is a vector, fixed vector, a point on this line, plus some alpha I. So x prime I only influences alpha I, and b and u are going to be common for all the points. Okay. So with this perspective, then if you want to go to put points on a line, then the objective is to choose the best b, u, and alpha, right? Alphas. So there's going to be one alpha per original data point, so we need to choose alphas as well. So we need to choose b, u, and alphas, such that something is small. And what is something? Which is the error. Okay, so what is the error? There's going to be an error per data point, and what is that error? So that's captured in this objective function here. So this objective function is the reconstruction error, which is the function of b, u, and alpha. So the moment I choose b, u, and a bunch of alphas, one for each data point, I already get a performance number, which is that, hey, for each data point, there is this original xi that that's the original data point. That's not something to vary. But there's also x prime I, which I am getting because I chose b, u, and alpha I in particular. So the difference between these two vectors, okay, so xi is a vector in some n dimensions, x prime I is going to be a point on this line, but in the same n dimension. So you can look at the difference, okay, between the vectors, and they're 2 norm square. Okay. This is just a candidate loss function. You can, sorry, candidate performance measure. You can also use anything else, but let's say this is the measure that we stick with. So for each data point, we're just saying, hey, because you chose b, u, and alpha I, there's going to be some error for each data point potentially. Maybe hopefully it's 0. If it's 0, it's fine. But if it's not 0, then this is a performance score. Now we want to figure out what is the b, u, and b, u, and alpha I that we can pick. Okay, so now what we did is define an objective. It's a objective which is written here. So we have this objective. We need to find b, u, and alpha. Alphas, there's no constraint. Alpha I for each data point can be positive or negative or whatever. It's just a real number. And the point b itself, again, it can be any point, and it just has a point in Rn. So b is also fine. U, because we want to ensure that there are not too many choices of u, let's fix it to be a unit length vector. Okay, so u can also be any direction, but it just has to be unit length, so that when I multiply with alpha with u, then it scales with 2 units, 3 units, and so on. Okay. So we have a quadratic constraint and a quadratic objective. The quadratic constraint, so it's quadratic because it's we're just taking the objective and the constraint to be like norm squares. So norm squares kind of lead to a quadratic objective and a quadratic constraint. with that, we saw last time when we were doing parameter estimation with the multinomial model, right? When we were doing the unigram language modeling, we saw how to define a Lagrangian when we were doing basically constraint optimization. This is a constraint optimization problem. So we have to define a Lagrangian, and that the first derivatives of the Lagrangian give us some necessary conditions of what any potential maximizer or minimizer would have to satisfy those necessary conditions. Okay. So let's look at first. Let's define the Lagrangian, and then we'll look at what properties does a solution has to satisfy in terms of Lagrangian. So what is Lagrangian? It's just the objective minus or plus. It's just a choice. So let's say minus alpha, so minus lambda times the constraint. Okay, constraint 2 norm square is just u transpose u, where u is that vector again in n dimensions. Okay, so this is the definition of the Lagrangian. Okay, and what we'll do before we kind of look at any optimal solution, any optimizing solution should satisfy some first derivatives of Lagrangian to be equal to 0. Set of constraints. Set of equations. So let's we'll just expand the Lagrangian for a second, so that we get terms which involve b, u, and alphas separately, kind of. So what we did, so 2 norm square again is just this is a vector xi minus b plus alpha iu, the vector. So vector transpose the vector. Okay, that's what gives you 2 norm square. And then you multiply element wise. It's just expanding brackets, and so you get this really long expression here. Now we'll use the if you remember from our last week, we used the Lagrangian to say that the derivative of the Lagrangian with respect to the parameters, we need to set them equal to 0, and a solution to the optimization problem should satisfy that those equations that come up, right? So I just copied the definition, the Lagrangian expansion that we did in the previous slide. This is the first summation here. And then now let's start setting the grade of the Lagrangian with respect to lambda, with respect to alpha I, and with respect to b equal to 0. Okay. Yeah. So we kind of ignoring u for a second, but basically if you take the gradient with respect to lambda, we just get back the original quadratic constraint, which is u transpose u is equal to 1. With respect, if you take the gradient with respect to alpha I, so there are going to be, in fact, we need to take the gradient with respect to each alpha 1, alpha 2, alpha 3, alpha little m. So let's say we take the gradient with respect to alpha I. That gives us an equation, okay, which relates alphas with u and b. Okay. It looks like alpha I is equal to u transpose xi minus b. It just turns out like that. Similarly, if you take the gradient or the partial derivative of the Lagrangian with respect to b, then you get an expression which gives you something like sum over alpha I times u is equal to sum over xi's minus mb. Okay, some relation between alphas, u's, and b's with some data also. So data is the xi's, okay, x superscript i's themselves. So what we can do for now is do some reduction. So if you just use the second and third equations, then what we see is that u transpose xi minus b. Yeah. So u transpose xi minus b. So xi minus yeah, sorry. So you substitute the definition of alpha here. So alpha I is u transpose xi minus b. So that gives you this expression here. So instead of summation of alpha I in the third equation, you get some term which involves summation, but it's now no more alpha there, times u. Okay, times u is here, is equal to, you can simplify, you can push the, yeah. You can take the mb, the m out, so that you can put a bracket around xi minus b. Okay, and u transpose, whether it's inside the summation or outside the summation, doesn't matter. So you have an expression like this. Now this term here, again, this is equal to sum of alpha I, right? this is equal to sum of alpha I times u, and that should be equal to the right hand side, which is sum of xi minus mb. So what we're trying to do is a little bit of arithmetic to kind of relate these unknown quantities, b, u, alpha, and lambda. So what we see from this plugging the second equation, third equation, is that, remember left hand side, so if you just focus on the last two terms here, in the one before the equality and one after the equality, this term here is just saying sum over alpha I times u. So you remember u is a vector. Sum of alpha I is a bunch of numbers, sum of them is another number. So the left hand side is some vector, right? So it's a some scaled version of u. The right hand side is also a vector, sum of a bunch of data point vectors, which is also a vector, right? So basically what we see is that u, the vector u, must be parallel to this summed up vector. Okay, so sum of xi's in a sense, sum of xi's as well as xi's minus b, that vector. Okay. So actually if you take m common, then there's a u has to be parallel to this averaged vector of the original data points minus b. Okay. So that's what I wanted to drive home in this slide. It's just that u has to be parallel to an average of the original data point vectors. Okay. Remember our original, just don't forget our original objective. We just want to ensure that we want to find the best line, okay, such that these points can be projected on these points. We get another point on this line, which is x prime of xi, such that it's the best line. Right? Best line was defined according to the loss function that we saw in the previous slide. So, so in this slide, a little bit of explanation is needed. So this just symbol double parallel just means it's parallel. So u is parallel to this vector here, which is nothing but the average of these vectors minus b. So actually this L, don't worry about it. So this L is actually, there's supposed to be a space between them. So just define L to be x bar minus b. So x bar minus b, where x bar is nothing but this 1 by m sum over m of xi. Let's call it x bar. So what I'm saying is that u has to be parallel to this x bar minus b. Okay. So let's think of what's happening pictorially. What we did with we defined the objective function, we defined a Lagrangian, we took its gradient, set it equal to 0. And then we found a property, which is that if you think of the line, let's say the line is this blue line, then, and the blue line will be defined by b and u, right? So every point here is b plus alpha u for some alpha. What we found is that this difference between this u has to be parallel to x bar minus b vector. Okay? So if you think of, let's say, this origin here at the bottom left, then this is the b vector, this is the x bar vector. X bar minus b will be this, has to be this, this line here, or this vector here, x bar minus b, which has to be parallel to the u vector. Remember, u has to be, so u vector is anyway in this direction. Okay, so that's what this figure is trying to show, which is basically that if u is parallel to x bar minus b, then x bar has to be on the line. Okay? X bar has to be on the line. And b is any arbitrary point is on this line, so why not just choose b to be x bar itself? Okay, so what we're doing is, in the original objective optimization problem, we have too many things to choose, u, b, and alpha i's. We just, from this discussion, what we can do is say that x bar must be on the line, so why not choose x bar itself to be b? Okay. That's what because remember, we have to define a line, we just need a point on the line. We just established that x bar has to be on the line. And so let's just call x bar to be b. Any questions here? Okay. Okay. So with that, since we, so what that helps us, from the previous slide is basically we can drop b from our discussion and just put x bar there. So the original problem was something like this: some quadratic objective, minimize that loss or some performance measure subject to u's being unit vectors, u being a unit vector, sorry. And we just said, hey, let's just pick b to be x bar. So we'll just have something like that. And alpha I, remember we already had a formula from the Lagrangian thing, which is alpha I should be equal to u transpose xi minus b. It just happens to be xi minus x bar. Okay? So with that, now we are getting to something which hopefully resembles closer to what you've seen with other discussions of PCA, which is that now we have an objective function which just involves the u, which will turn out to be principal common direction, but u and the data. Okay, so the data is appearing in this bigger bracket in the center, which is u transpose xi minus x bar and xi minus x bar transpose. So it's some sort of a matrix here, okay, times u, such that u is the 2 norm square of u is equal to 1. Okay, so this is the new objective function we got because of the previous observations, where alpha is related to u and b is related to x bar. So all the b is also related to data points. So this is the new objective function. And with this objective function, if you take the gradient with respect to u for this new quadratic problem, the quadratic objective and quadratic constraint problem, if you take the Lagrangian and take the gradient with respect to u, this is a quadratic function of u. So if you take the gradient with respect to u, what you get is 2su. Okay, this we are accepting as a fact here. You actually want to show for any matrix, any objective function like u transpose au, where a is some matrix. If you take the gradient with respect to u, then this vector gradient that you get should be equal to 2 times a times u. Okay, so that's what's happening here. So 2 times s times u is something you should test offline. So 2 times s times u, and then this term used to be u transpose minus 1. So that give a term like this. Okay? So what that essentially gives us is you set the gradient equal to 0. Then that gives us the expression s times u is equal to lambda times u. Okay? Where what is s? S is nothing but this term in the center of this in the second expression optimization problem, which is xi minus x bar times xi minus x bar transpose. Okay, so that's a matrix. Okay, that's a rank 1 matrix. Yeah. So is the middle term a covariance matrix? Yes, it is a scaled version of the covariance matrix. We'll just define that. We'll just kind of give a name for it. It's not exactly the covariance matrix, it's a scaled version because there's no 1 by m in the front. So we'll talk about it in a second. Okay. So what we found is that if we want to get a line and points on the line, so like a proxy for each of the points on the line, right? That's what we want to get. Then we can just solve this optimization problem, get a u, and once we get the u, then each alpha I is just u transpose xi minus x bar. Once we get alpha I, we already know b, we can get each point. Remember our original objective was for each original xi, we want x prime I, and x prime I we said is just b plus alpha I u. For that, somehow we, not somehow, but we saw through previous, discussion that the original problem can be transformed to a problem which involves only u, and then if you take the gradient with answer equal to 0, you get a problem which should be familiar already to some of you. It looks like a eigenvalue, eigenvector type of problem, but we'll talk about that in a second. But S here is a scale version of the covariance matrix. Okay, so S is just each data point. So first of all, add up all your data points, get a final, averaged vector. From each data vector, subtract that vector. So you get the, new vector. Then take an outer product with it. Okay, this is an outer product. And then sum up each of the outer products. Okay, there will be a little m number of outer products. You sum them up. That's S. Okay, that's also a function of data. As Shiva mentioned, so it's called the scatter matrix. Okay, it's just for simplicity, if you don't want to remember another term, it's just a scaled version of the empirical covariance matrix. Okay, so covariance matrix for a n-dimensional vector. So if you have an n-dimensional random variable, right, let's say 10-dimensional random variable, then the covariance matrix, or the covariance of this random vector is defined as a matrix. Right? So we have seen that for multivariate Gaussian distributions. Right? Generally, for example, we would represent that using the letter sigma. So sigma, which is covariance of a random vector, would be the vector minus its mean vector times the vector times the random vector minus its mean vector transpose. Okay, so it's the outer product of x minus mu of x and x minus mu of x. So this should also be capital X here. That's outer product, and then expectation with respect to that. So, so that's how you would find the covariance. And so I think you can ignore this because you don't have a y here, but mu of x is just the expectation of this random vector. Okay. So remember, if you have multidimensional Gaussian, let's say two-dimensional Gaussian, then mu of x would be two numbers, okay, in two dimensions, right? So and the covariance matrix would be a 2 cross 2 matrix. Okay, so that's what you'll get, and this is the definition for computing that. And so S is nothing but a scalar multiple of the empirical covariance matrix, because S, if you just do 1 by m times S, that's an estimate of your covariance matrix. That's a candidate estimator of your covariance matrix, and it has its own properties of how good it is and what is its quality and so on. Okay. So now let's focus on our original problem. Again, remember we wanted to project our points onto a line. So we want to see, okay, we want to find a u such that S of u is equal to lambda u. Right? And so that's the u that, that's the, in any u which, has to satisfy this equality. And we also know originally that u also has to be a unit vector. Okay. This problem here, we want to find a u such that S of u is equal to lambda u, and u is a unit vector. That problem is exactly the eigen matrix S. So lambda and u are nothing but the eigenvalue and eigenvector pair of S. Okay. And S is given by the data. And firstly, you may say, okay, so there's an eigenvector. So first of all, the definition of an eigenvector eigenvalue is that if you multiply a matrix with that vector, then you get back a scale version of that vector, right? So, if you remember from your prereq linear algebra notes, that's, this is true. And then generally you want to scale your eigenvectors to be unit norm, because otherwise you can always keep multiplying them, and they're not unique that way. So we just want one eigenvector eigenvalue pair here. Okay. So one question that we can ask right now is that, hey, is lambda, which is an eigenvalue, is going to be real? Is it going to be a real number? Okay. Turns out, if not all matrices have real eigenvalues, okay, and they may also not have positive eigenvalues. So the question is here for this problem, for this our problem, which we identified as a eigenvector problem. What does lambda look like? Okay. It turns out that lambda is actually real and non-negative. Okay. Why is that? And the short answer, don't worry about the dual feasibility part. It's not critical here. If you just look at how we have framed this problem, can we find a u and lambda such that this holds, such that u is unit norm? The data part is S, right? So it turns out S is actually a symmetric positive semi-definite matrix. Okay? It's a symmetric matrix, which means that if entry ij, it's equal to entry ji. Okay, so it's going to be the same value. And it's also positive semi-definite. Okay, so that's the property for some matrices, that they are positive semi-definite. So S has that property, and because of which the lambda is going to be real as well as non-negative. Okay. So, and you want to check why S is symmetric, not just symmetric, but also positive semi-definite. You can just look at the definition of S. Okay, S is like this. That turns out that it doesn't matter. So from this expression, you can actually make out that all its eigenvalues are going to be real valued, and they're going to be positive, or non-negative. So we are not going to look at that detail right now. But lambda is, happens to be real and non-negative. Okay. Now the question is, what is u, right? U. Remember, we wanted to, in the original problem, we want to maximize this objective. Okay, which means that we want to maximize u transpose SU, right? So u transpose SU is what we want to maximize. And so we just don't want to satisfy SU is equal to lambda u. We also want to find that u and lambda pair such that u transpose SU is maximized. Okay, and that's exactly is the definition of the first eigenvalue and first eigenvalue eigenvector pair of this matrix. Okay, so so which u will maximize u transpose SU is the eigenvector associated with the largest eigenvalue of this matrix S. Okay. So the largest eigenvalue if it's the largest eigenvalue, then the eigenvector associated with it is the one which maximizes U transpose SU. Why is that? Okay, so let's think for a second. So why would finding U which maximizes U transpose U correspond to that U which corresponds to the largest eigenvalue? Why is that? It's easy to see that because remember, if you're going to maximize U transpose SU, remember SU is equal to lambda U, which means that we're maximizing U transpose lambda U, right? And lambda is a scalar, so just bring it to the front. Then you just have lambda times U transpose U, and U transpose U is just unit norm, right? So if you want to maximize this objective, then you better pick the lambda which is the highest. Okay? So therefore, we are actually picking the highest eigenvalue and its corresponding eigenvector. Okay. So we picked the highest eigenvalue and we found its corresponding eigenvector. Now we already have a solution. We have a solution to the original problem. We have a solution to this problem, therefore we have a solution to this problem. Okay. So what is our solution? It's that U, okay, the U, which is the eigenvector corresponding to the largest eigenvalue. And that eigenvector, we're going to call it the first principal component direction. Okay, so the first eigenvector direction is the first principal component direction. This is just definition of the eigenvector that we found. That's the direction which is the first principal component direction. Any questions with this derivation so far? We'll look at some illustrations to further ground our intuition here. In fact, in the next couple of slides. Okay, so let's look at some illustrations. Okay, there's a question. Does the largest eigenvector capture the maximum information variance in the data? Yes, and that's actually a great question. We'll look at some illustrations to kind of really identify that aspect. Yes. So, we'll answer your question. So show me in a second. So, what does each of our observation mean? Let's actually come back to some basic linear algebra for a second, and then come back to your question, Shubham. So let's revisit what an inner product means, right? So if you think of an inner product between two vectors, u and z, it's just defined to be the norm of u times the norm of z times the cos of the angle between those two vectors. Okay. Or cos of theta is just the inner product divided by the norms of the two vectors. Okay. So in pictorial terms, you have a vector z and you have a vector u. Then it's the vector z's projection onto u. The projection onto u is just the norm of z times cos theta. Okay, so this length here, which is in black, is just you want to say, hey, z is this vector, but how much of it is represented by the vector u is just a norm of z times cos theta. And if u is actually unit vector, then u times this inner product is actually just turns out, if you use unit vector, then you kind of lose this part, right? So norm of u is 1. And so inner product is exactly equal to norm of z times cos theta, which is what exactly we said here in this illustration. In particular, so if u is unit norm, then unit norm or this 2 norm is equal to 1. Then this inner product just gives us the length, okay, this length of the u directional component of vector z. So this vector z, it's u direction component. So if you project it onto u, then there's some constituent of z which is in the same direction as u. What is its length? Okay, that's what an inner product is doing. It gives you. Right? So now let's come back to our formulation from 2 slides ago. We had this maximize this quadratic function subject to a quadratic constraint. And we said, in fact, the inner bracket is actually equal to S, right? The scatter matrix. So let's look at this optimization and then talk in terms of this inner product that we just saw in the previous slide. So you have this xi, and each of the xi is getting subtracted by x bar. So we are subtracting from each data point. Then what we're doing, so essentially what we've done is zero-centered each data point, in the sense that each of zi is just xi minus x bar. Is zero-centered in the sense that if I take the average of all these zi points is equal to 0. Because if you take the sum of zi's and divide by 1 by m, which is the sum of the right-hand side, and sum of the right-hand side, it's exactly, it just turns out to be 0. Right? So that's what zero-centered means here. So if you kind of recast the problem in terms of z's, what you're seeing is you have this original objective, right? U transpose this thing here. It's going to be U transpose Zi transpose U. Okay, so where the summation, I've just pushed it out. So it has nothing to do with U. So U can be kind of brought in. So U transpose Zi transpose U. Right. So we just kind of just change of names of variables. So instead of xi minus x bar, we just call it Zi. So we just have this new expression here. Now, if you look at this expression, this is nothing but the inner product. So the first two terms are the inner product between U and Z. And next two terms are the inner product between Z and U, which is again symmetric. So it's just the same as the inner product between U and Z. Right. So it's the summation of U and Z and U, right, which is nothing but U and Z, the whole square. Right. What we've kind of observed is that our original optimization problem just turns out to be a sum of a bunch of inner product squares. Okay? And when we're trying to maximize this objective, right, when we're trying to maximize this objective, remember each of this U so each of this U comma Zi, this inner product, remember when our U is unit length, this inner product of U comma Zi is just the length of the U component, U direction component of Z's. Right? So we just saw it in the previous slide. This is just these lengths that are being captured. Right? So we are trying to find a U such that these lengths are as long as possible. So we are just trying to find a direction U that maximizes this sum of lengths. Okay? And so with that context, we can answer Shubham's question. So let's see. So what if this U? Okay? Remember, U has the interpretation of the largest eigenvector. But what is this U? Let's say U is perpendicular to a direction which I'm calling as the data stretching direction. Okay. So these data points. So in this figure, again, two-dimensional figure. So our data points are these crosses here, cross. There are 5 data points, for example. And I just picked a direction which just happens to be something, is perpendicular, as in like a different direction than much of the data stretching direction, which is in the direction which data seems to be spread out. Okay, that's all it means informally. So if you take this as a potential candidate U, then you can see that each Z, right? So if you each Z, like let's focus on Z1, each of the Z's, its length according to along the U direction is just this. Along the U direction is just this. So if you think of a triangle, like a right triangle here, so the Z cos theta basically is this red for Z1. Similarly, this data point, Z cos theta will be some triangle here, and then this will be the length. Okay, remember that's will be the length. So if you think of the sum of these lengths are not, it's just a bunch of red lines on the same direction as U, but sum of lengths here. Okay? In fact, that happens to be the smallest if you pick U perpendicular to the data stretching direction. Okay? So it'll be pretty close to 0. Now contrast that with the setting where I'm picking U to be parallel to the data stretching direction. Okay? So something parallel to the data stretching direction. So U is like this. Then you can see that when I project U, so let's say Z1 is being projected onto U. So I want to know how much is the length of Z cos theta, Z1 cos theta, for example. You can take a triangle like this. So go from origin to this cross, and then think of how much of Z is being represented on U as a length. You can see it's pretty long. So each of the Z is actually pretty long in terms of how much they're represented along the U direction, right? And so if you add them all them up, it just turns out that this direction, which is in the data stretching direction, is going to lead us to the highest sum. So, this I guess hopefully answers Shubham your question. The principal component direction is the most stretching direction of the data. Okay, at least the one we saw in 2 slides ago. Remember, U was the eigenvector corresponding to the largest eigenvalue, and then we interpreted what does U do? What do different choices of U do? The choice of U that maximizes the objective is a U which is in the direction where the data is the most dispersed. Okay. So for example, if you run PCA on the example that we saw like several slides ago when we were talking about the line approximation of the original data points. For example, if you have original xi, x3, for example, you somehow want to get a point on the line which approximates that original thing. Then all these points have to kind of be projected onto this line. This line is basically b plus alpha u, where we said b is equal to just the average of the points, and u is the large, eigenvector corresponding to the largest eigenvalue of the scatter matrix of these data points. Yeah. So any questions here? We just kind of we're trying to give the intuition which Shubham asked, which is does the largest eigenvector capture the maximum information or variance in the data? It does. I didn't mention information or variance yet, but you can see that this is basically in this direction. Basically, you have long line segments, so that is basically going to capture the variance in the data. We didn't talk in terms of variance, but that's what it does, at least in terms of pictures. Any questions before I move on? Okay, so we went through a lot of particular path to get to this interpretation of the largest principal common direction. Now we're going to generalize it a little bit more to get to the full principal common analysis procedure. But before that, what have we seen so far? Principal common direction is the most stretching direction in the data, at least for the line version, line approximation or line dimensional reduction problem that we saw earlier. And x prime I is the projection of xi onto the principal common direction. In fact, it's the orthogonal projection onto the principal common direction. What do I mean by that? So remember, again, each of the z's or xi's, you have to project it orthogonally. Orthogonally just means perpendicularly onto the principal common direction. Okay, and wherever that hits, so the x hits, that dot here is the z prime, or in general x prime. Okay. So x prime of I is the orthogonal projection of xi onto the principal component direction. So what are its implications? So far what we've seen is what is the principal common direction, the direction which is most stretching the data. In fact, we're focusing on only one direction. We're going to generalize that in a second. And x prime i's are just orthogonal projections of xi's onto this direction. Okay. So what are the implications currently? Given this original data points without labels, we evaluate the scatter matrix. You saw that it's just each data point minus the mean data point, auto product with itself. That will give a matrix. You just average out all these little m matrices. That's a scatter matrix. And then do an eigen decomposition of S. Okay? Eigen decomposition of the scatter matrix just means find its eigenvalues and eigenvectors. Okay? So eigen decomposition, what does it do? So if you have an original matrix S, which in our case is also actually positive and semi-definite. It's positive, semi-definite, and of course by definition also it's symmetric. Then it's the eigen decomposition just means that S is being broken down into three matrices. Okay? So the first, the matrix is basically U lambda U transpose. So basically, what is this first matrix? It's just the collection of eigenvectors. Okay? The second matrix is the collection of eigenvalues, which we remember are non-negative, and they're on the diagonal. Okay? And the last matrix is just a transpose of the eigenvectors matrix. Okay, so instead of arranged as a row, arranged as columns, they're just arranged as rows. Okay? So that's the definition of eigen decomposition, where we are choosing a particular order. The order we're choosing is the first eigen or the largest eigenvalue. Okay, largest. Remember these are all non-negative. The largest means exactly. There's no confusion that there's a negative eigenvalue which has higher magnitude or anything like that. Lambda 1 is like something like 100, or lambda n could be 0 or 0.1 or something. Okay? So we are choosing this order that lambda 1 is the highest eigenvalue. So therefore, the corresponding eigenvector, which is little u1, is the first principal common direction. Okay, is the principal common direction for now. Okay? In fact, u1 is the most stretching direction by definition, since lambda 1 is the largest. Okay? And u2 is a direction which, because of eigen decomposition, is going to be orthogonal to u1, okay, and is the next most stretching direction. Okay? So it's just by how eigen decomposition plays out that u1, so u2 has to be orthogonal to u1, and is going to be the next most stretching direction. Okay? So the third point basically is the same side as before, except the third point is that the eigenvectors of the empirical covariance, whether you take the eigen decomposition of S or whether 1 by m times S, you will still get the same decomposition. Okay, so it's just a scaling difference with the 1 by m in the front, okay, which is a constant. So the eigenvectors of the empirical covariance matrix provide our principal common directions. Okay, so that's the observation here. So now let's actually state everything in terms of a general k-dimensional setting rather than this one-dimensional, like projecting all these points into a line was the view we saw. Okay, so far. We're gonna just change that to what if you want to project it into a low-dimensional space. A low-dimensional space is essentially nothing but a hyperplane. Okay, so what do we do? So we want to generalize. So we want to go from our original data points to a little k dimension vectors. Okay, so little k dimensional. So little n dimension to little k dimension, which means we were going to project all these original little n dimension vectors to a hyperplane. Okay, so what is that hyperplane? That hyperplane, let's call it b plus alpha 1 times u1 plus alpha 2 times u2 to alpha k times uk. Okay, so this is the definition of hyperplane. Hyperplane in the sense that this equal to 0 is going to be, actually no, this itself is the definition of hyperplane according to our previous way of discussion. So b is a point, and each vector from that point, right, it's going to span some region of the space. If it doesn't span the full n-dimensional space, then that's basically a hyperplane. Okay? And again, so these u's, we want them to be orthonormal. So orthonormal just means that they are perpendicular to each other, and they are normal vectors in the sense that they are unit vectors. Okay, so it's meaningful exactly because of the interpretation that we have here. We want to have use orthogonal, and so that we can get this explicit stretching definition that, hey, the second stretching direction is. Okay. So from what we saw with the one-dimensional, where we're only trying to find the most most stretching direction, the generalization to the k-dimension setting is as follows, right? So b is still the same. X bar of I, so x bar basically. This is average of the data points. And u1 to uk are going to be the top k eigenvectors. Okay, top k in the sense that look at the eigenvalues, take the top k eigenvalues, and then corresponding eigenvectors will be the eigenvectors. Okay, so that's u1 to uk. And then our xi prime, which is the new point, okay, which is our new point, is going to be take the original point and project it down to onto the hyperplane. But remember, this hyperplane is composed of all these orthogonal. It's basically a combination of these orthogonal vectors. So you can project the origin point onto each of these each of these unit vectors, which happen to be orthonormal. And so this lambda j, so okay, this is a minor comment here, which is this the eigenvalues themselves give a sense of the variance, how much variance has been captured in in each principal component direction. Okay, so lambda j in fact is the variability of the data captured by the jth principal component direction. So we can choose the dimension k based on how big or small the lambda k values are or lambda j values are. For example, if you take the first little d principal component directions, then which means a d-dimensional representation of the original n-dimensional vector, then the amount of variability you're capturing is it's going to be up less than 1 and greater than 0, between those two ranges, and so it's going to be lambda 1 sum of the first d values, the eigenvalues, divided by all the eigenvalues, sum of all the eigenvalues. Okay. And so you can see whether, hey, adding one more eigenvalue is adding, is making us, is there a bang per buck or payoff for adding one more dimension to your reduced dimension. So if there's a big drop between lambda k and lambda k plus 1, that means that k plus 1 is not really adding much if you include that as one extra dimension in the when you do the dimensional reduction. Okay. Any questions here? You can use a mic if you want. Okay, so let's actually look at the 4 examples that we saw at the beginning. So these are 2-dimensional examples. So of course, we are trying to only get to potentially dimension 1 here. So here you can see, this is just illustration, so they're not exactly look orthogonal, but you can see lambda 1, for example, and lambda 2 happen to be 0.09 and 0.0007. And so yeah, so you can see that maybe, because there's a huge drop between lambda 1 and lambda 2, you can think of, maybe one-dimensional, one principal component direction is enough. Similarly here, with even though this is a slightly weakly data set, you can still see that lambda 1 versus lambda 2, there's a big drop off. So you could potentially, if you want to reduce dimensions from 2 to 1, you could just focus on the first dimension. Okay. Similarly, if you look at the third example from before, which was the basically circle with some noise on the circle, for this lambda 1 versus lambda 2, you can see that both are kind of very similar to each other, 0.08 and 0.07. So it's basically saying that you cannot reduce variance irrespective of what direction you pick. Okay, so it's still going to be you're still in a second direction. Okay, so it's not really a good variance reduction happening if you go if you pick only one dimension, because lambda 1 divided by lambda 1 plus lambda 2 is approximately 50%. So you're only, by going from 2 dimension 1 dimension, you're losing 50% of the variance here. And that's clearly not suitable. As you can see, there is actually a low dimensional manifold, which is a circle. And if time permits, we'll briefly mention what we can do. And in particular, what we can do is actually, we can use something called kernel PCA. Okay. And finally, this is the last example where there was no structure. And so here again, you can see that there is no gap between lambda 1 and lambda 2. Again, it shows that there's not much advantage in going from 2 dimension to 1 dimension, because you're not capturing all the variance in the data. So you're only capturing 50% of the variance in the data. Any questions here? Okay, there is a question. Is there some standard range of values to decide what is considered a big drop in lambda k versus lambda k plus 1? Off the top of my head, there's actually no such heuristic. There may be such heuristics. Actually, as you know, there are always heuristics to choose number of clusters that you might have seen in other classes. Um, so here, yeah, there's no particular preference that I am aware of, but I'm sure that people have a sense of what could be some heuristics, rules of thumbs that you can use. Yeah, but I don't remember. So I don't remember any particular that I can recommend at the moment. Yeah. Okay, so we'll make a couple of remarks. Which is that uh, firstly, so we've actually done PCA. PCA is essentially we did the computation procedure behind all this is just take the scatter matrix or basically the empirical covariance matrix, do an Eigen decomposition. Okay, so that's you can do it by numpy dot I think EIG, I guess, is the routine. I don't remember exactly, but basically you can get the Eigen value decomposition. And if you have really large data, okay, so really large covariance matrix, then there are more numerically efficient ways to compute the top k eigenvectors than doing some naive way of doing eigenvector eigenvalue computation. Okay, so there's some numerical efficiencies that can be gained by being clever with how you compute eigenvectors and eigenvalues. But once you do that, then you essentially got principal common directions, and all you need to do is now project the original points onto these directions. Um, so that's the computation procedure. But there are a few comments to make, which is firstly that if you have a data set and there are some, and if you kind of imagine them in an n-dimensional space, and if there are points which are far away, okay, so points which are far away from the others, they can have an outsized impact on the empirical covariance matrix. Because remember, empirical covariance matrix, there is always a outer product term for each data point. And so if the data point is far away from the mean vector for the data set, then that will have an outsized impact on the covariance estimated covariance matrix, and that can have a big impact on the choice of your principal common direction. Okay, and so there are ways to robustify your dimensional reduction approach. So one simple heuristic, again, this is there's no particular recommendation as such, but or it's not a very objective recommendation, but you basically discard some outlier points. So basically something, and this is something you would do with pandas data frames, right? If you think of a data, if you describe your features, you kind of see some sense of like, hey, some data points, some rows I can drop, right? So maybe something like that would help. Here, the recommendation is you can drop points that are far away by looking at pairwise distances if you want. But there are many ways to drop what you can heuristically call as outliers, right? So you should do that. Second thing is you should also deal with different coordinates, different attributes of your original data can have different dimensions, and if you change the dimension, you can increase or decrease the absolute magnitude. And so they can actually, of course, they will influence the results of your estimation. So to deal with that, you can normalize each input Okay, so yeah, now since I restarted, I don't know if I saw somebody's question, but hopefully, if there's some question that I missed, then I'll repeat it here. But basically, what I'm saying is that the SVD of a matrix, of a rectangular matrix, is related to the eigen decomposition of the matrix times its transpose. Okay, so that's the first bullet point here. So if you think of SVD, then you get U sigma V transpose. It's related to the eigen decomposition of ZZ transpose. Okay? ZZ transpose happens to be a positive singleton matrix, and so it will have a decomposition which involves the same U and the same sigma. So it turns out, and it's a minor detail, that instead of doing eigen decomposition, because you will have to construct the empirical covariance matrix, it's better to work with the original data matrix and just do SVD on it. Okay? And the SVD itself also can be scaled up if you have too many data points or too many dimensions. So here are some example applications. So when we have too many features, so that's, as the name suggests, we are reducing dimensions. So you can pre-process your data and reduce the dimensionality of your original data points, and then do any downstream task. And typical downstream task is going to be something like supervised learning, prediction of a target label, or you can also do clustering and so on. Okay, which is part of your assignment. Or the second, application is when you are, you are actually trying to somehow shrink the amount of data that you have. For example, here you can see that the original data is actually images, and so you can actually somehow reduce the dimensional data such that it still retains much of the characteristics of your data. Then as long as it retains enough characteristics, then you can just use that as some sort of a compression of your data. Right? So that second point is really not that different from the first one. It's just saying that you're basically focusing on compressing your original data point and reconstructing it. And that's also one application. Yeah. So so far PCA, as you saw, is all about projecting an original data point in our n dimensions to a hyperplane in k dimensions, or a line. Line is what we kind of spent a lot of time on. Can we project down to a, or can we get a lower dimensional representation where the lower dimensional representation is not linear? Okay. For example, here in this case, if you do PCA, then and then you think of, hey, I want to go from 2 dimensions to potentially 1 dimension, you can see that you cannot really do that because you're not capturing much of variance in your data. But there is actually, you can see that this is actually a circle, so there may be another way to do that. And we have not really spent too much time on this particular trick because we didn't spend too much time on SVMs. But the idea comes from what we saw with SVMs, okay, what we would have seen with SVMs, which is with SVMs, there's a way to go from talking about SVMs, which are linear SVMs, which you worked on extensively in your assignment, to nonlinear SVMs. Okay? So nonlinear SVMs give nonlinear decision boundaries, and the way you achieve it is using a kernel trick. Okay, so where instead of giving the linear kernel as a parameter, you give a nonlinear kernel, like a polynomial kernel or other kernels as a parameter. Similarly, you can use the kernel trick to get to a nonlinear projection instead of a linear projection of your original data points. Okay? If we have time, we will discuss that. So let's pause here for about 10 minutes and resume. And what we'll do next is briefly recap k-means and then talk about density estimation as a topic. So let's resume at 4:40. Okay, so let's resume. I hope people can hear me. Wow. But I have a trouble sharing. Okay, so what I'll do is now talk about a different problem compared to the previous problem, which was about dimensionality reduction. Now we're going to talk about density estimation, but there's going to be a twist. Okay, so we've seen density estimation in various forms before when we're estimating the parameters of a multinomial distribution, or parameters of a Bernoulli, parameters of a Gaussian, and so on. Now we're going to try to make it a little bit more challenging. Okay, and that will be in the context of density estimation for unsupervised learning. And so what is the sequence? So we've seen k-means last time. We saw principal component analysis just now. What we're going to do is look at mixture of Gaussians and then look at a particular technique called expectation maximization. Although I want to talk about mixture of Gaussians, density estimation, and EM, I'm going to briefly recap k-means because there's going to be a relationship. We can contrast k-means with EM as a technique. Okay? So k-means for clustering, EM for mixture of Gaussians. Both techniques have some similarities and differences. So we'll briefly mention that. And so for that, I want to briefly recap k-means. So k-means, if you remember, is a clustering approach. So what is clustering? You want to assign different data points to different groups. Right? And so here's a two-dimensional example where the algorithm itself, to get to these groups of different data points, the algorithm starts with some initial candidate cluster centers or centroids. So here you can see the blue, red, and purple centers being one of the data points, like 3 different data points here. And then given the initial candidate centroids, you look at all the points which are closest to it, the centroids, the squares, and then just call them belonging to that cluster or that group. Right? So for example, the closest to this red box or this red data point is this other red data point. So whereas all these ones are close to this blue one, and so they are the assigned the blue cluster label, and similarly this one being the purple one. So and then once you have these new cluster labels, then you ignore the previous cluster centers or cluster centroids, and then focus on re-estimating the new cluster centroids. And they are just the average of the points in your current cluster. So since these are blue, you just take the average of those blue points, and then you get a new square, which is blue over here. Previously it was here, and now it's moved down. Right? So similarly, the red one and the purple one. With those new cluster centers, again, you estimate the cluster labels, and then again update the cluster centers, and so on. So once you do that, you will reach, when you do this iterative new cluster center computation and new cluster label computation again and again, eventually you may reach a point where the cluster centers will not change or will not move too much, or the cluster labels will not change at all. So yeah, so at that point you can stop, and that's your example grouping of your data points. Okay. So here's the same description that we saw with the illustration. So we start with some initial cluster centroids, mu1 to mu k, either random, or you can pick one of some k points in your data set to be the initial centroids, and then you start assigning. Right? So given these data points, the closest ones to it, given the centroids, the closest ones to it are assigned that appropriate cluster label. And then once you have the cluster labels, you assign new cluster centroids, which is just the weighted averages, or just the average of the points which belong to the appropriate cluster label. Like little k is the cluster label, then all the points associated with it are taken. You take a simple average of them, and that's the new cluster centroid. Okay. Any questions about k-means? It's pretty clear. We've discussed it at length last time. We're just checking if there's a question about k-means. Okay, so k-means was a nice technique to cluster. Now what we want to motivate is a density estimation technique, but it's motivated by an issue with clustering. Okay, so clustering, for example, what k-means does is what is called hard clustering. Okay? Hard clustering, or it's again informal. Hard clustering just means that each point belongs to only one of the clusters or the groups. Okay, so um, um, for example, each of the points in this yellow circle belong to exactly the yellow group and nothing else. For example, what happens to this red point here, right? So it's in this group, but it's kind of outside as well. It's closer to the yellow, I guess, cluster, as well as close to the red cluster. So basically, there's some issues with hard clustering when each point only belongs to one cluster. So in contrast, think of a situation which may be a little bit more appropriate in some settings, which is when clusters can overlap. So here, clusters are not overlapping except for, if you think of like drawing some sort of a nice shape around it, so clusters are not overlapping. That's what we mean here in these two dimensions. In some applications, clusters could overlap, right? So for example, here are two clusters where one cluster is overlapping with the other cluster. So a point inside the little dark red or brown circle is also part of the bigger cluster, and some points are not part of both the clusters, right? So there is some issues that crop up when you do hard clustering and you can't capture overlap, for example. Okay? So distances can be deceiving. So just because something is close by, right? So here, for example, maybe although it's close to red and yellow, it's unclear where it needs to lie, right? So distance can be also deceiving. So what we want to get to is basically that each point, we don't want to assign it to a single cluster. We want to say, hey, it could be 60% belonging to the yellow cluster, maybe 40% belonging to the red cluster, something like that. That's what we want to aim towards. Okay. And so in particular, what we want is a soft clustering method. Soft here just means that we want to assign each point, hey, that this point exactly belongs only to this yellow cluster and nothing else. Instead of saying that, we want to say, hey, this point belongs some percentage or with some probability to the yellow cluster, with some probability to maybe the red cluster or the blue cluster. Okay, so that's what we want to say. That's what is meant by soft clustering here. And so measuring distances, when we say distances, distance of the clusters to the yellow blob or the red blob or the blue blob. If you think of the distances in terms of like distances of centroids, you measure them in some sort of with a score. Probabilistically just means you assign a score between 0 to 1. Okay. So how do we do that? So how do we achieve soft clustering using some sort of a probabilistic approach? Okay. So what we'll do is one example to do soft clustering, which is going to be similar to discriminant analysis that we saw 2 or 3 lectures ago. Okay. Of course, in discriminant analysis, we had to have labels because of the supervised learning approach. Here we don't have labels, but we kind of retain some assumptions from there and build a soft clustering approach. Okay? And that's achieved via a generative model, which is called the mixture of Gaussians. And there's going to be a hidden variable involved. Okay? Just like hidden Markov models had hidden random variables, here there's going to be hidden random variables as well. Okay? One hidden random variable per data point. Okay, so let's understand what the generative process is. So the generative process is as follows. So we're going to assume that our data comes from a mixture of k Gaussian components. So k Gaussian components just means there's k Gaussian distributions, and each data point can come from any one of these Gaussians. Okay? So for example, so the way we're going to specify our generative process is that there's going to be k Gaussians, and we're also going to have a multinomial distribution, which means it will have a parameter phi k. And what the multinomial distribution first says is that what the multinomial distribution does, it helps us in getting this generative story, is that first we'll draw a sample from the multinomial or the categorical distribution. Okay, it'll say, hey, component 1, component 2, component k. Once you get the sample, once we know which component we want to, what component realizes, then from that component we generate a data point. Okay, so first you get a sample from the multinomial, it will be a number between 1 to k. Okay, let's say if the number is 3, then you go to the third Gaussian component and draw a sample. Okay, the third Gaussian component will have its own mean and covariance. Okay, so mu k and sigma k. Okay, so that's the generative process. And the difference from k-means is going to be that there's going to be a soft assignment of any data point. Okay, so any data point, if there's a data point, that data point could be, we're not going to say that it belongs to only one of these mixture components. So we don't know. So for example, if there's a point here, we don't know whether the point was generated from mu1, from the first component or the third component, or even from the second component, right? So there's going to be a soft assignment of any data point to any of these Gaussian components, because we don't know how the data got generated. I mean, we're telling the generative process and we already observed the data. We don't know for each data point how it got, whether it was generated from the first component, a second component, a third component, we don't know. So we assign a soft membership. So as a consequence of that, we'll have overlapping clusters. So overlapping clusters, it just mean that if you think of like drawing cluster boundaries, hey, this collection of points are predominantly belong to component 1, and this bunch of points predominantly belong to component 3, they may overlap. Okay, so there could be points which predominantly belong to both component 1 and component 3, for example. So that you kind of quantify that using a bunch of scores. So that's what probabilistic measurement here means. And just think of them as weights. Okay, so since there are 3 clusters here, so any point on this with a 3 cluster, 3 mixture component, 3 mixture of Gaussians, just means that any point will have like three weights. Okay, 3 numbers, not weights or scores, 3 numbers which kind of say, hey, 90% chance that it came from component 1. 10% chance that it came from component 2, and 0% chance it came from component 3, for example. Okay. Any questions about hard clustering versus soft clustering that we are going towards, or the generative process? Okay. So let's, before we continue to talk about the mixture of Gaussians, we'll briefly contrast them with Gaussian discriminant analysis that we saw a couple of lectures ago. It's a Gaussian mixture model, right? So it's only looking at the x's, the input features, if you want. So xi's in the data set, so we have little m of them. And the generative process is described in this two-step process, where first you generate a mixture, which mixture does the current point belong to, which of the mixture components the current point belongs to. Then, given the mixture component index, you go to that component and draw a sample. Okay, so those are these 2 steps. So you draw zi's from a multinomial distribution with parameters. So these are the parameters of this model, phi k, 1 for each of the k components, capital K components. And then xi given z is z being equal to k is drawn from a normal distribution with a mean and a covariance. Okay, so the mean and the covariance are also parameters of this model. So the total number of parameters is phi k, mu k, and sigma k. 1 for each component. So if there are 10 components, there's going to be 10 such triplets. Right? Gaussian discriminant analysis, if you look at the linear discriminant analysis case, it's very similar. It's for each data point xi, yi in the data set. So yi is the supervisor signal that we have. What we do is choose a label. So the z, instead of z, we are talking about y. Y is also a realization from multinomial distribution. It will also have parameters pk, but y is kind of assigned or kind of now defined to be the label. Okay. And given the label, each of the data point xi, given the label, comes from an appropriate, if the label is equal to k, then it comes from the kth normal distribution. Okay, so mu k, and linear discriminant analysis means that the covariance matrix is the same irrespective of the mixture component or irrespective of the which normal distribution you're picking up. But if you do quadratic discriminant analysis, then each of the component will have its own covariance matrix. Okay? So so if you look at Gaussian mixture model versus Gaussian discriminant analysis, the description is actually pretty much the same, except there's only data point xi, at least but there's only data point xi which are realized. But there is an intermediate random variable which is nowhere described in the data, right? So data doesn't have that random variable, but we are hypothesizing that we're going to have that random variable first and then generate xi's. Okay? Okay? That's the GMM process. In GDA, we actually got xi's and yi's, and so we hypothesized that yi's are first generated according to multinomial distribution, and then xi's given yi's come from appropriate normal distribution. Any questions here? Okay. So they are almost identical, and the question is which is a harder problem in the sense that harder learning problem. Okay? So and why? And we'll briefly try to answer that in the next 20 minutes or so. Okay? So brief, I guess, a recap on multivariate Gaussians, because we've seen them several times, but it's good to kind of know what they are. So the univariate Gaussian, when x is a one-dimensional random variable, it's is drawn from a distribution with mean mu and variance sigma square. Then its probability density function of p of any given value x given mu and sigma square is defined according to this formula. Okay, so the formula has an exponent and a negative square term and a variance term in the denominator and so on. And if you have the multivariate version, it looks almost same as the univariate version, except that the exponent will have a inner product. It's going to be an x minus mu transpose sigma inverse x minus mu transpose. So this expression should look very similar to the x minus mu sigma square inverse x minus mu. Okay, so one-dimensional version and the multidimensional version actually have the same functional form as long as you pattern match and see that, hey, there's no big difference between what we're doing with the one-dimensional versus the n-dimensional version. Okay. The only difference is that the multidimensional version, the covariance matrix must be positive semi-definite. Otherwise, this inverse is not going to work. Okay, it cannot be. Sorry, the variance covariance matrix. Yeah, it must be positive semi-definite. Yeah, there is a problem with inverses and positive. Just saying positive semi-definite. Let's say for simplicity, assume that it's positive definite. Okay. Any questions here? Okay, so quick visualization so that it helps us understand the estimation of Gaussian mixture model. So a unit Gaussian, here's a simple illustration. So you have a mean, and here's the width of the Gaussian probability density function is kind of at least here is showing as a 2 sigma band somewhere. But basically the if the variance is low, then it will be more peaky. Okay. Similarly, the multivariate Gaussian will look like a bump in a 3-dimensional plot. And multivariate Gaussians, to develop a little bit more intuition of how the distribution looks like. Here on the left side is a distribution where there is no correlation. There's no correlation between the first coordinate and the second coordinate. So it's a 2-dimensional Gaussian. So each coordinate is a random variable, and so how much is it correlated with the second coordinate is given by this covariance matrix, right? So it's 1, 0, 0, 1 is an identity matrix, which means that the 2 coordinates are independent of each other. And similarly, you can see that the moment they start being more and more correlated, this Gaussian bump becomes, kind of elongated. Okay, so you can see that it's getting elongated in this case because of the way the covariance structure looks like. It's getting elongated, along the 45-degree line, but it could be in other ways also. Okay. Okay, so it's not just in the previous figure it was just exactly elongated, being elongated in the towards the positive orthant. You can also shift it such that it's actually being elongated along the minus 45 or minus or 135 degree axis, and it can also be further elongated that way, or it could also be bigger, right? So if the sigma has larger entries, then the bump is not peaky but has higher variance, and so it's more diffused. Okay, so that's what this figure is showing. Okay, so briefly want to mention the variance covariance matrix or the covariance matrix. So that covariance matrix sigma, as you know, if it's positive semi-definite or positive definite, then you can break it down into U lambda. So this inverted A, A type of symbol is capital lambda, U lambda, U transpose, as this Eigen decomposition of this matrix. And this decomposition is exactly what you would do if you had the original data matrix, right? If you had the original data matrix, you could compute the empirical covariance matrix and then solve, get the Eigen decomposition, and then you get the principal components. So here, if you just have the covariance matrix, it always decomposes this way, U lambda, U transpose. And then lambda and U's kind of define the new bases, right? So U1 and U2 are these two bases, and lambda 1 and lambda 2, their square roots kind of give you the length of how much the elongation is in these two new basis directions. Okay, so U1, for example, is in this direction, and lambda 1 to the power 1/2 kind of tells you how long the ellipsoid is in that direction. Okay, it's the axis length, or half the axis length. Okay, so any questions about that? I was just trying to give you a quick recap on Gaussian distributions. We've seen it several times before, but it's good to kind of really understand it. Let's say 2-dimensional, 3-dimensional version. If not, let's actually move forward. So what do we need to do now? So we just described the Gaussian distribution, Gaussian mixture model, which is nothing but has parameters phi k, mu k, and sigma k. And now, given a data set, if we can fit these parameters, then we can assign soft clusters. So then we can assign for each data point a cluster membership, which is basically soft membership, which means that each data point doesn't necessarily belong to only one cluster. It could belong to multiple clusters or groups, okay, or components in our case. So so the parameters are listed here. So it's basically phi, mu, and sigma. So phi, if you remember, it's a parameter for multinomial distribution. So if you have k components, capital K components, then there's going to be k minus 1 independent parameter. Similarly, mu, remember, there's one vector per multivariate Gaussian, and each vector is n-dimensional, so n times k. And each sigma, if there's only one sigma, each sigma is going to be an n cross n symmetric positive semi-definite matrix. Since it's symmetric, it's n times n plus 1 by 2 is the number of unique parameters in each one, and there's with capital K of them. Okay, so that's the total number of parameters. And if you write the joint distribution, distribution of these of the data points not just the data points, the data and okay, yeah, let's just we like the likelihood of the data. Okay, likelihood of the data D. That's going to be functions of these parameters phi, mu, and sigma, right? So where we just kind of said mu1 to mu k, let's call that set to be mu, and sigma1 to sigma k, let's call that set to be sigma, right? So if you write the likelihood of this data, right, what is in fact log likelihood of the data, then the log likelihood is going to be sum over I is equal to 1 to m log of the probability of each data given these parameters, right? Now, this is a marginal distribution on x's, but we know from our generative description that we know what the joint distribution of the x's and z's are. Okay, so we can use, we know that the marginal is equal to joint divided by, the marginal p of x is equal to p of x given z times p of z, and then average out the z's, right? So let me see, is this correct? Sum over, yeah, so this is correct. So what we're doing inside the log is just looking at the joint distribution between x and z, and then averaging out the z random variable. Okay, so z takes k, capital K different values, so we're just averaging out the z values. Okay, so this is the joint distribution. This is the expression for the marginal distribution, and so this is the likelihood. Okay, so we wrote likelihood. What we did is on the left hand side there is no z on the left hand side, But on the right-hand side, we introduce z, because z is part of our generative process, for which we know, for example, probability of zi equal to k given phi, we know what this probability is. It's exactly equal to phi k. Right? And probability xi given zi is equal to k, we know what that is. It's a Gaussian distribution with mean mu k and covariance matrix sigma k. Right? So the question is now, and the reason why we're studying mixture of Gaussians as an example today is this is where things diverge. So this expression, this likelihood, looks similar to Gaussian discriminant analysis. In Gaussian discriminant analysis, we're not maximizing the likelihood of just the features or just x's. We are maximizing the likelihood of x's and z's. Okay? So it's a little bit different, but at the same time similar. Okay. Since it's similar to Gaussian discriminant analysis, you can ask a question: can we simply do maximum likelihood estimation by differentiating this likelihood, this log likelihood? Okay. So if you remember maximum log likelihood, of course there is an issue of constraint with the sum of phi equal to 1. But in a model of that, everything else, can we just take a derivative set equal to 0 and get the parameters? And the answer for Gaussian discriminant analysis, which kind of holds for mixture models, this Gaussian mixture model, is that yes, you can use MLE and use that to estimate parameters only if you know the hidden variables, okay? Which means that only if you know the hidden variable z's, their values. Okay? So for each data point xi, if I know the zi, okay, which means now I have bigger data. If I have that more complete data, then maximum likelihood estimation is easy to use, and then it'll actually give you the formulae for the phi k, the mu k, and the sigma k. And it turns out that these formulas are exactly the same as the Gaussian discriminant analysis case in the quadratic version of it. Okay, so it's actually, in fact, you can kind of just see that the formulas at the top and formulas at the bottom, you don't have to parse them. The only difference is that instead of y's, there are z's at the top, and at the bottom there are y's. Okay. So if you observe these, then the problem is kind of easy, because we already saw that when we're looking at the quadratic Gaussian discriminant analysis case. Any questions here? Okay. So, but the challenge is that we don't know z. Okay, so if z is known, then Gaussian mixture model estimation is the same as Gaussian discriminant analysis. But z's are not known. Okay, z's are hidden variables, and so we don't observe them. So the data doesn't come with z's. We are thinking that there are z's in the data. There should be z's which kind of determine how the data got produced. Okay. We are going to use a technique which is the EM algorithm that kind of guesses what the z's are and then updates the parameters. Given the parameters, updates its guess of what z's could be, and again guess the parameters and so on. So there is an alternating update on what z's could be, and given z's, basically kind of use these formulas. If I tell you what z's are, you can use kind of these formulas or something similar to it to estimate the parameters. And given parameters, you can re-estimate what z's could be. Okay, so that's what the EM approach does. And I want to briefly mention that in general, that's how it works for not just for Gaussian mixture models, for any other latent variable model. Okay, so latent variable model just means a model in which there's there's going to be a distribution of random variables, of which some of the random variables are latent, as in they're not observed. So for any latent variable model, for example, there's a model called restricted Boltzmann machine, okay, RBM. It's also a latent variable model. For example, for any latent variable model, you can use a technique like this, where you can do something like EM, where you can say, hey, what are the likely values of the latent variables? Okay. You can try to guess that. Once you get the guesses, then you have a complete data, because you have a guessed latent variables and the observed variables. Now you have a complete log likelihood. Maybe you can maximize that likelihood, get some parameter estimates. Given the new parameter estimates, again, try to make a guess of what the latent variables could be, and so on. Okay, so that procedure is shown here. So it's called expectation maximization algorithm, because the two steps that I said, this guessing and then estimating, is called expectation and maximization steps. Okay, so the E step is about guessing. Okay, so E step, we are basically getting an estimate. Okay, so we're getting a vector. Okay, we're getting a vector Wi for each data point I. This vector is saying, hey, with what probability, what is the probability with which Zi is equal to k? Okay, given the current parameters and the data point, can you tell me what is the likelihood that this Zi is equal to k? Okay, Zi can be 1, Zi can be 2, Zi can be 3, Zi can be all the way capital K, right? So then there's going to be k such numbers. Okay, each of those numbers is called W subscript k to the superscript I for the ith data point. So you kind of get k numbers which tell you what's the likelihood that for this data point xi the Zi is 1 or 2 or 3 or 4 or k. Okay, so that's the E step. And the M step is, once I tell you what my guess is for z random variables. Okay, remember z are supposed to be just memberships in one of the components. Okay? Z could be one of the components, but here w's are guesses. So they're saying, hey, with some probability z could be 1, with some probability z could be 2, and so on. Now with these w's, what you can do is now estimate the parameters of the mixture model. Which is phi's, mu's, and sigmas. Now, what changes from the previous slide is that you're going to use the w's corresponding to each component to estimate, for example, the mu and sigmas. So remember, so for example, if you focus on the formula for mu, for the kth component, it's just saying that, hey, with some probability, the ith point belongs to the kth component. Okay, that probability is actually wk for the ith component. Okay, so and there's going to be wk for each of my little m data points. If I have 100 data points, each of the 100 data points can belong to the kth component, kth Gaussian, with some score, with some probability, right? So maybe the probability is, for some it may be 0, maybe some it's very small values, for some it's maybe large. Okay, so I'm just going to do a weighted average of all points, okay, where the weights are now determined by my E step. Okay, so that's going to give me my mu k. Similarly, sigma k is again a weighted average of these empirical covariance estimates that I'm doing. Okay? And phi k is just the proportion of each cluster component. That's just the sum for each kth component, how prevalent it is. Okay? So any question about this E and M step for the Gaussian mixture model? Okay, so now, I want to wrap up, although the slides have a little bit more derivation of why EM works, I will try to not cover that because we're running out of time. But I want to just contrast this with k-means. Okay, so if you remember k-means clustering, so k-means for the clustering problem was giving hard assignments, as in a point should either belong to one group or the other group, or one cluster or the other cluster. Okay. Whereas Gaussian mixture model, inherently, when you think of a data point can come from the first Gaussian component, second Gaussian component, third Gaussian component. It can come from any Gaussian component. So you kind of say, hey, with what probability can come from each component? And that's what basically even the E step is doing. Okay. So you can actually match the E step to one of the steps of k-means, and the M step, the maximization step, to another step of k-means. Okay? So E step is, E step for us is giving a best guess estimate of the cluster membership. Okay, so it's actually saying, hey, with what probability does Zi, which tells us the cluster component membership, with what probability is equal to k? Okay, so for Gaussian mixture models, we are actually getting a best guess for the soft cluster membership. Okay? Whereas the M step is updating the parameters based on the new membership. In the k-means case, the M step was giving the parameters happen to be the cluster centroids. Right? So in the M step, given the cluster memberships, we are getting the new cluster centroids. And in the E step, we are getting new cluster memberships based on the current centroids. Okay, so that's exactly what's happening in the E and M step in the Gaussian mixture model case. Actually, let me show in terms of the procedures themselves. One is for clustering. The other one is estimating a density, because once you estimate the mixture of Gaussians, it's actually a density estimation that you've done, because you've estimated the density of this multimodal distribution of your data, right? But that estimated density, after computing mixture of Gaussians, you essentially get clusters also, because once you get the mixture of Gaussians, if let's say the capital K Gaussians, then basically those kind of correspond to your K clusters. So with that in the background, you have the two techniques very similar. So in the E step for K-means, you first get hard cluster membership. So argmin would be, hey, a data point, if it's close to one of the centroids, then that centroid's label is this cluster label. That's what's happening in the E step for K-means. Whereas the E step for Gaussian mixture models, it's saying, what is the probability that you belong to any one of these K components given the current point and the current parameters? Okay. You also have a current parameter. Mu K is a current parameter. Here, there's phi, mu, and sigma sets, right? So here you have a soft assignment in the E step. And the M step, given the soft assignment, so given the hard assignment for K-means, you are getting new cluster centroids. Whereas in the Gaussian mixture models case, you, for example, if you focus on mu K, for example, you are getting an assignment, a new assignment for the component means, which is basically similar to the centroids. These mu K and this mu K are kind of analogous to each other. You're getting an assignment of what the new mean vector for the kth component is, for example. Okay? So you're getting new parameter estimates given soft assignments. You're getting new parameter estimates given hard assignments. So that's how these two are related. Yeah. So the next few slides, at least in the deck, they talk about how to how to reason about EM, right? So why does it work? I'll briefly mention a couple of points, and we'll kind of wrap it there. So EM algorithm has a similar flavor to K-means in terms of alternating iterations, right? So we learn both cluster membership and model parameters. But it turns out that because we are not observing all data, right? So in our model, we're saying there's an xi and there's also zi, right? So the hidden latent or the latent variable or the hidden random variable, okay? For each one value for each data point is missing, which means that our likelihood function, it just turns out that the likelihood function of likelihood of a data set, it's a messy function, and that's why we have this iterative procedure, the EM procedure, and we can't use maximum likelihood estimation directly, okay, when we don't observe ZIs, right? which is our case. And so when we optimize, when we do this EM approach, it's an iterative approach. It's like doing gradient descent on the messy or gradient ascent on the messy log likelihood function directly. So if you did not want to think about EM, you can think of, hey, directly, how do I maximize this log likelihood function? Okay. Since, as I said, the log likelihood function is messy in the sense that it's not convex, for example, right? You may get to some local optima, and the same is true even instead of doing gradient descent. If you do EM, you will be iterating over parameters, and you'll get to some final parameters, maybe such that they don't change, for example, just like in K-means case, the cluster centers don't change or the cluster labels don't change. But that's not the global optima. In the K-means, it's the same issue. You can get to local optima. Same thing with EM procedure for Gaussian mixture models. You'll typically get to local optima. It's very hard to figure out whether you are at the global optima or not. Okay. So yeah, so that's, I guess, the main point I wanted to make. With that, let me, last couple of comments. So one is the number of Gaussian components is in user input. There are variants of these methods, both for, variants of these methods, which can adaptively change K as a function of growing and growing data size. For example, today you had 100 data points, tomorrow you have 1,000 data points. You can go from, let's say, 10 clusters to 20 clusters in a seamless way, but that's beyond scope for today. For this model that we just saw, K is a user input. Number of cluster components is a user input. Okay. So here's an example from a real data set. So this is anemia patients and controls. where having an overlapping cluster representation makes sense. Okay, so it's RBC concentration and RBC volume. It's actually almost 20 years old. So you can see you can start EM and start EM with some parameters. So here are the two. So we chose the number of components to be 2 here, and so the green and the red show two different. So show two components that are kind of pretty much overlapping with each other. And as the EM iterations proceed, so third iteration, these two components look like this, fifth iteration, they look like that. And you can see by 10th iteration, they have a, the two components overlap. Okay, so these two are Gaussian components that overlap. And you can see that at some points, they're part of both clusters, okay, in the sense that, every point is part of both clusters. But for example, at some point here, we'll have very low probability of being in the green cluster and pretty reasonably higher probability of being in the red cluster. So this is an example where hard clustering would also maybe make sense, but may not. It's unclear how it will deal with the points which are between these two clusters, the red and the green. Okay, so what I will do is not go over the derivation for EM, which is there in the slides. I'll encourage you to look at it. Just use the same ideas that we saw before when we were analyzing other techniques, except for one or two extra tricks. But the analysis shows that expectation maximization is alternating alternating maximization approach, is essentially very similar to gradient descent, actually very similar to gradient ascent, okay? A particular gradient ascent technique, and it will converge to a local optimum. So although it's alternating approach, iterative approach, it's expected to converge, okay, somewhere, in the sense that you will get to some optima. It just happens to be, we cannot claim that it's a global optimum. So that's the only issue. I was going to briefly mention what the techniques, a couple of other problems in the unsupervised learning landscape. One of them is independent component analysis. The other one is canonical correlation analysis. I will skip that in the interest of time. So I would suggest look at the next slide deck, actually, lecture number 12. And if you have any questions, reach out to me. Any questions about what we covered so far today? Okay, so let me just wrap up by summarizing what we saw today. We actually went through a journey of looking at a simple, a particular view of principal component analysis in terms of projecting a point onto a line and getting a sense that, hey, that projection, that line, the direction has to be kind of the direction which stretches which is in the direction of the data, stretched direction of data. Basically, the direction is also supposed to be the direction corresponding to the largest eigenvector, the eigenvector corresponding to the largest eigenvalue of what is called a scatter matrix. And then we kind of generalize that, okay, if you're trying to project a point to a single line, that's what happens. If you're trying to project it to, if you're trying to reduce dimensions to k dimensions, then you basically take the top k eigenvalues and their corresponding eigenvectors will give you the new basis. Okay? In that basis, you can have a data point representation, and that representation will be capturing as much variance of the original data set. Okay? And you had to do some subtraction of the mean and normalization. There were some tricks that were mentioned. And in the second half, we briefly looked at density estimation, and one particular density model, which is a mixture of Gaussians. Makes sense pretty much only for numerical data, but just like discriminant analysis, but gives you a sense of soft clustering. Okay? This is not the only approach. There are other approaches which also give soft memberships to or multiple memberships to each data point. And we saw mixture of Gaussians, how it relates to Gaussian discriminant analysis, how it also relates to k-means via the in terms of at least the estimation approach, which in this case was expectation maximization approach. And it's a tool that is, you already know maximal likelihood estimation and how to solve MLEs using taking derivatives equal to 0 or using gradient descent. Expectation maximization is another tool you can use if you have what is called a latent variable model. And Gaussian mixture model is an example of that, where the mixture, which mixture does each data point belong to, is kind of hidden or unknown. Okay, so that's what we covered today. In the next lecture, the slots for each group are already assigned in the spreadsheet. We'll pretty much start, and there are some instructions on the project page and the spreadsheet. So let's look at that, and the class will be online. And so we'll look at your project presentations. Okay. So with that, let me end for today. If you have any questions, please stay back and we can discuss as well.